So it's not only the final work of the session, it's the final work of my PhD with my excellent PhD advisors, Avigdor and Erez Karpas, who couldn't make it today, as you know. And so today what I want to show you is a brief explanation of what goal recognition and goal recognition design, which I call GRD, are all about. I'll show you the current GRD framework, which kind of reflects the lessons that we have learned since our first ICAPS paper in 2014, where we coined the term goal recognition design. Then I will show you how generalized strong stubborn sets are used for goal recognition design. So Marcel was very helpful in presenting that framework. And then I will show you new modifications that can be applied for GRD thanks to this formalism. And the second speaker actually was right to the point in that respect, so thank you. I don't have any relationship that I can think of to Daniel's talk, but 2 out of 3 is good enough. I'll give you a short explanation of our evaluation and some conclusions. So goal recognition design, what do we want to do? Consider this setting where we have agents that are acting in the environment, and for the sake of discussion, let's assume these agents are optimal. Now, these agents are trying to achieve their goal, and while observing them, we try to recognize what they're trying to achieve. Now, if we assume these agents are optimal in a fully observable setting, if we look on the agents on the right, we can assume that they are going to the right door, right? If we assume that they are going to either the left or the right door, the agents on the right are going to the right door, and the agents on the left are going to the left door. The problem is caused by the agent in the center. Not only is she not revealing her goal to us, she can actually walk all the way up to the wall before revealing her objective. This is the situation which we focused on when we started my PhD work, and we defined the measure which we called worst case distinctiveness. How far an agent can progress in a system without revealing its objective to the recognition system. So worst case distinctiveness evaluation is the first stage. Then the second stage, given this evaluation of the model, we try to think of ways to modify the environment in order to get an optimal setting. So in this case, minimize the worst case distinctiveness. So we can apply modifications to the environment, and of course we can build this wall. And by building this wall, we can enforce the agents to reveal their objective as soon as possible. Now, in this setting, in this specific setting, we are assuming agents are agnostic to the recognition task. But this same idea can apply to suboptimal agents in a setting where agents want to conceal their objective. The framework, as I will show you next, has been generalized, but the essence is portrayed here. This is a solution that achieves minimal WCD, but it's a suboptimal solution in the sense that we can apply less modifications, we can intervene less, and achieve the same result. So what we are looking for is the minimal change that needs to be introduced into the model in order to achieve minimal worst case distinctiveness, and in this case, this translates into modifications that can be introduced into the environment. For example, here we have, I don't know if you can see it, this beautiful fountain in the entrance of the terminal or in the entrance of the room that encourages or minimizes the worst case distinctiveness given the assumptions that we make on agent behavior. So this is actually a slide that I presented in ICAPS 14, and what we established there is a process where we have an environment, we have assumptions that we make on the agent, we know what modifications can be applied, we first find the worst case distinctiveness, and then we find the optimal design policy. Okay, so we're seeking for an optimal modification sequence that minimizes the worst case distinctiveness. So applications are abundant wherever goal recognition is relevant and modifications can be applied. Goal recognition design is relevant, intruder detection, smart homes, e-commerce, and my personal favorite is human-robot collaborations. In these settings, there is a clear need to understand what humans are trying to achieve and vice versa. Humans want to know what robots are trying to achieve, and we can change environments in order to enhance this recognition. Okay, we don't have to assume that the environment is given to us as input and there is nothing we can do. Sometimes we can introduce small changes to improve this ability to recognize the goals of agents. So this is kind of the evolvement of our framework throughout the years. We started with optimal agents. We followed by a work on suboptimal agents. We then focused on non-observability from the point of view of the system. And then we showed that our models can be adopted to privacy-preserving agents. So the worst-case distinctiveness behavior can be adopted by an agent that wants to obfuscate his objective. As you can see, we were joined by many others. Son has developed, or Son and his collaborators have developed a solver for goal recognition design using ASP. They beat our methods, but only for fully observable agents. I'm waiting to see how you deal with the partial observability. Mirsky et al. Presented a framework for plan recognition. Christabel and William have worked on fully observable environments with stochastic actions. We are currently working on extending this model for partially observable states, and goal recognition design has been adopted also to an adversarial setting. So we have our work on privacy preserving, but Masters and Sardina have worked on deceptive path planning, which is greatly related, and sorry, I can't pronounce his name. Ang et al. Have worked on game theoretic goal recognition models where they apply the goal recognition design framework. So as you can see, there has been extensive work. Most of the work so far has focused more on the definition of the models, on the formulation of the measure, and how to compute them. And at least we devoted much less attention to the design process. So as a final stage of my PhD, we wanted to kind of like give focus to the design process. And one of the lessons, so there were many lessons that we've learned doing this. And one of the realizations that we came about was the fact that the goal recognition design can actually be viewed as a search. And what does this search, or basically what it does, in order to do that, we first need to define the elements that comprise our model. So the goal recognition design problem has two components. The first is the goal recognition model. The goal recognition model is basically a planning domain where we have a set of fluents, an initial state, set of actions, and as opposed to a planning problem, here we have a set of possible goals. And in addition, we need to account for the way the agent is perceived by the recognition system. So we have an observation tokens and a sensor model. All of these create the goal recognition model that we want to analyze. The second element is the design model. The design model defined what are the modifications that we can apply to the environment, the atomic modification, the transition function defining what would be the effect of a modification, and a constraint function. Now, defining this already allowed us to view the constraints that we imposed so far in a more general context, but also the behavior of the agents in a more general context. We now account for arbitrarily defined plans. So we want to detect, given a goal recognition model, we want to detect non-distinctive behaviors, that is, behaviors that are shared by multiple goals. We want to calculate the worst-case distinctiveness, so the maximal non-distinctive path in the model, how far, what is the maximal progress an agent can take without revealing its objective, and find an optimal modification sequence. One of the painful lessons, and now it's a very helpful lesson, but as you can, during a review process, this was very painful to discover, we realized that we were a special case of a more broader problem called environment design, which was actually coined by Zhang, Chen, and Parks, where they defined a more general problem of, given a set of modification, what would be the optimal modification sequence to apply, given the utility function. So the utility function in our case is the worst case distinctiveness, which is hard to compute because, and as I show you in a minute, we calculate the worst case distinctiveness by compiling our problem into a planning problem. So we use classical planning to calculate the worst case distinctiveness. To me, this is super cool, but out of scope of this discussion. I only mention this to remind you that when we look at the search, each node in itself is extremely computational demanding, so we need to find a way to make our search more efficient. Okay, so this is the core of this talk. what we have realized, and again, this is something we applied in ICAPS 14, but only in retrospect did we realize that what we were actually doing when we were doing design is a search in the modification space. Okay? So on the top part, what you see is the design space, where we move between modifications. The transitions are actions, are the modifications that we can apply. And the leaf nodes here represent the goal recognition models. So when we design a problem, we are actually transitioning between goal recognition models. And again, in 2014, we applied we compared our exhaustive reduce algorithm, which examines all modifications, to a prune-reduce approach. The idea in the prune-reduced approach is that we look at the current WCD path, so the path that maximizes utility, maximizes the worst-case distinctiveness, and consider it. So only the actions that affected the WCD path were considered. So this was what we did in fact. What we did not realize is why is this working? I mean, we didn't think about why is this working, and to figure the benefit of figuring out why this is working is going to be apparent, I hope, in a minute. Just I want to mention the fact that the WCD path that we rely on for our computations are found with no extra cost. So as Marcel mentioned, when we want to calculate strong stubborn sets, sometimes the overhead of just figuring them out is computationally demanding. For us, the strong stubborn sets are just part of our calculation of each node. So it's kind of like something that we can, it was a very, I wouldn't say easy, it was definitely not easy, but once we figure out that we have strong stubborn sets which comply with the framework that Marcel presented, we can use them to not only make the models that we already created clearer, but we could extend our models. And I will show you why. The thing that we realized is that what created a model that was easy to, that was prunable was the fact that our models were independent, persistent, and monotonic, non-distinctive. So we could account for all our previous model, but also define new modification methods. So strong stubborn sets, I'll only mention this briefly because we heard about it before. Strong stubborn sets in the context of design provide us the guarantee that for every node that we look into in the search, the modifications that are not pruned include the first modification in an optimal sequence. Okay? In an optimal sequence, we don't have a goal. What we are trying to reach is we are trying to reach a node with optimal WCD under the constraints that we are aiming for. So in our context, and we adopted the terminology by, sorry for the wrong pronunciation, Werl and Helmert. Independent in our context is the same as Marcel presented. Application order is not important. Persistent means that our constraints are persistent. We cannot have an invalid modification cannot be a prefix for a valid modification sequence. And non-distinctive paths are not added to the model. Okay? What this allowed us to do is to enrich the goal recognition design framework with new modifications that could be applied. So the easy one was single action sensor refinement. When we add sensors to the model, when we increase observability, we are definitely improving recognition. This is kind of easy to show. What we did in addition, as opposed to the first model where I showed you where we disallowed actions, so creating the fountain disallowed actions, in this work, what we did, we introduced constraints into the model. So kind of in reverse to the second talk here, we take a partial order and we enforce it into our plan. So for example, in this setting where we have this robot, I unfortunately don't have the time to show you the whole example, but the idea is that if we disallow an action here, if we have a robot here that is trying to achieve one of two goals, the idea is that if we don't modify the environment, block D needs to be moved in any case, okay, for the achievement of any of the goals. So disallowing any of the actions will make the problem unachievable. The thing is that we can force the agent to first pick up block B, making sure that if block B is the first action to be removed, we know that the goal is goal 1, because block B does not need to be removed. How do we enforce that in practice? We make sure that the robot cannot, after it extends its grip, it cannot close the hand again. So it starts in a position where it can pick up block B, but after he extends the hand to pick up block D, he cannot contract it anymore. I hope that's what you say. So basically, what we introduced here is a more refined a modification that deals with creating a partial order. In this case, I enforce the agent to, if he needs to pick up block B, this is the first action that he will perform and reveal its objective to the recognition system. So, I don't think I have time for the empirical evaluation in depth, but what we showed and was, of course, we showed that pruning was effective. Due to lack of time, I won't go into the details. I'll just say that we tested this domain on IPPC domains and the ISS domains with non-uniform action costs, yes. And the idea was that by introducing the more refined action conditioning, in some cases we could achieve the same results as we did with action removal. So I don't think we have a lot of time for your complaints. Maybe we do, but I thought maybe you would have some complaints, so I wanted to think about them ahead of time. The idea was to show you the Go recognition design framework, to how we use strong stubborn sets to make sure that the pruning we perform are safe. We extended Go recognition design by introducing the options, first showing why previous models worked, and introducing new modifications into the environment. So I thought maybe your complaints, potential complaints would be that our assumptions are quite restrictive, so assuming modifications cannot add non-distinctive paths, so not add new paths to the model is quite restrictive. Yes, that's true, but nevertheless we account for all previous models on Go recognition design that have previously been presented and offer new modifications. Tighter envelopes, indeed. Excellent idea for future work. We consider the whole space, but there's much more to do in this respect. Thank you.
Thank you. Questions?
Well, thanks for the presentation. I presume that the observation tokens in your goal recognition model are perfect observations.
Oh, no, not
no.
no.
You can have noisy observations.
I
mean, wrong observations.
Yeah, no. We support noisy sensor models. So non-deterministic sensor model with noise and non-determinism. Yes, our models support that.
And I was just wondering in that case if, let's say, fixing the noise observation could be also considered as part of changing the environment.
Yes, that's what
besides adding constraints to the environment.
Yes. So this was what I referred to as sensor refinement. Maybe I should elaborate on that more. So sensor refinement is indeed exactly what you said. So I put a camera in an area where I have noisy observations, or I improve the quality of the camera, and I have a predefined budget of where to put them. So the Go recognition design framework will tell me where I should put the camera in order to make sure that the WCD is minimized. Thank you for that. I kind of...
Thank you.
Thanks.
Yeah.
So what happens in your initial example if you've got an absent-minded traveler that wanders past, right, and then realizes it, and they were looking at their cell phone and they back up and come back around.
So
is this a case in which your initial computation would give 4 as a number, and then it would get revised at a later time?
So what you just described, we refer to as bounded suboptimal agents. So we are talking about agents that may divert from optimal behavior, but to some extent. And they may get tired after a while, and they may realize that they're out of path. So we don't support, well, the general model supports arbitrary paths, as long as you can give a measure for goal recognition. But the models that we support for worst case distinctiveness computations are bounded suboptimal agents. So they have a budget that you can define as part of the input for diverting from optimal behavior, and we can kind of, maybe a fountain is not enough, maybe we have to extend it to make sure that even those agents that you just described will nevertheless follow distinctive behaviors to their goals. Did I answer that question?
Yeah, does this have any impact on your more recent modifications with the use of the stubborn sets and
so what?
the bounded
No. The framework for strong stubborn set is kind of decoupled from what you are referring to, which is the computation at each node. So what would be mainly affected by what you just described is the computation of the value of the nodes. The worst case distinctiveness would be harder to compute because the set of possible plans is increased, but the overall search is not affected. Still you have, given the methods or the WCD computation methods, the overall search remains the same. Not the effect, but the overall search and the benefits of using generalized strong stubborn sets. It remains the same.
We're a little bit over the time, so maybe the last short question? No? Then let's thank the speaker.
Thank you.